Um, we will start the next presentation. Um, the presenter is Patrick Stakem from Capital Technology Institute of Technology. All right. This is your. You need to hang on to that. Yeah, I think that is good. Just put that click on.
Testing, testing.
Yes, you have to test.
Okay. Testing? Can you hear me okay
Yep,
in the back?
That
Hello?
sounds good. Sounds
Okay.
good. And this is the clicker.
Okay. Okay. I wanted to mention that I work for Johns Hopkins, not for the lab here, but for Hopkins University. This particular project that I'll talk about, which is a strawman mission that we defined during a summer session for undergraduates, senior undergraduates, and a couple of grad students over at Capital Technology University, which is the second best institution of learning in Laurel. Their advantage is, A, they built their campus a mile from my house, and they're about 5 miles from Goddard with a high-speed data line coming over. So they have an entire control center that they use to train operators. A few of my students have gone through that, and they're spacecraft operators now over at Goddard. But this came from the second session that we did over there. The first session also resulted in a paper that I presented at the last flight software conference here, having to do with Control Center, the Cosmos product from Ball, integrated with CFS. Not to start this out on a commercial point, but it was recommended to me that I mention that I wrote a couple of Cubesat books based on my experiences in teaching. I wrote one on Cubesat engineering, which is how to build a Cubesat, Cubesat operations, which is how to fly it, one on Cubesat constellations, swarms, and clusters, which is how to use a bunch of them together, and another on interplanetary CubeSats, which is what we'll talk about, one of the aspects that we'll talk about today. And then I wrote another one, I had too much spare time, on STEM. I've most recently started developing some material for STEM educators so they know where to get the detailed information that they need to teach STEM projects. And yeah, last year my grandson built his first CubeSat, and that went pretty well. And we'll see how it goes this year when he shows up for Christmas. But then again, he's smarter than I am. Okay, so this project resulted from a, where's my clicky thing? Set down. Resulted from a student-based project over at Capital. Most of my collaborators on this project were students in the program. They're all back in Brazil right now. With these projects, we continue them if the students have an interest. So I am actively collaborating with them in Brazil. And the last guy there was my communications guy, setting up the inter-satellite communications and also the communications back to Earth. And by the way, he just graduated with his PhD and he's looking for a job, and he is really good. So part of the complexity of the problem, if you take a look at something like Jupiter, you can make a chart of this for all the different planets, 67 moons, somewhere around 1 million Trojans, which are essentially moons in the same orbit. And they're pretty big. And then there's the various ring systems. There's 4 distinct rings. There's probably more smaller ones. And the other problem there, well, besides the radiation environment, the other problem is the one-way light time is fairly extensive, although that seems like a good number to the New Horizons people because they're still sending their data back. So the project, okay, we're at a summer Cubesat course. Generally, I let the students self-organize, get in a little group of 4 or 5, come up with the project they wanted to do, and then implement it. And this particular project was a project I wanted to do, so I selected 4 or 5 of them and said, here's what we're going to do. And as I mentioned, it's continuing. The program was kind of interesting. Brazil had a scientific mobility program with competitive exams. So you could take these exams. If you're one of the top scorers, you got all expenses paid, plus tuition, room and board, spending money to go, not just the United States, but any major university you wanted to go to. So it was a pretty good program. And what it meant was the students that showed up were the best of the best. And I tried to exploit that as much as possible. Unfortunately, due to some political problems, this program is no longer in effect. So my supply of Brazilians has been cut way back. So it's crowded out at the Jovian system. There's a lot of stuff out there, most of which we haven't looked at. At the time the Juno mission was on its way, by now it's, I think it's completed end of mission, I'm not quite sure. But anyway, it took 5 years to get there. Yeah, arrived in 16. Let's see, it's in an interesting orbit. It takes 53 days to orbit. It's chosen to minimize contact with the radiation belts, which are a huge major problem, making the Van Allen belts look like a fairly benign environment. All of its electronics, it has triple Rad 750s. All that is in what they call the radiation vault, which will give you an idea of the problem. And the interesting thing about one of the interesting things about the Juno mission, it uses solar arrays. There's some new, very high efficiency solar arrays. There used to be missions past Mars used radioisotope thermal generators, which are fairly difficult to get the paperwork for to be able to launch them. But now they're able to use solar power at Jupiter. So it has a launch mass of over 3,000 kilometers, 3 big solar panels, but they're only receiving about 4% of what they would receive at Earth. Still, it's enough to keep it going. The closest distance to the planet was about 4,200 kilometers, and it's in a very eccentric orbit, shall we say. So Juno itself has a series of instruments to take a look at the planet in different wavelengths, both infrared and microwave. They're looking for water and water ice. We know that exists in some of its moons, atmospheres, and also underneath a surface of ice. It's looking at the magnetosphere, particularly the auroras that form in the high latitudes. It uses X-band to get back to Earth, 50 megabits a second. There is a constraint between that and the amount of onboard storage and how many images it can do. So it's limited somewhat in how much data it can collect. It uses a bipropellant system for insertion into orbit, and then a monopropellant system for attitude control. Why am I talking about Juno? Well, I got kind of interested in this mission, and almost all my students were either computer science or electrical engineering, but I had a perfectly good mechanical engineer, so why waste that? And I said to him, take a look at the profile of the Juno mission. the size of the shroud, and the weight, and tell me how many Cubesats I could put on that mission, just as a little, interesting experiment. So I said make the Juno the Cubesat dispenser, we'll call it the mothership, and it'll also be the data relay back to Earth. Anyone want to take some guesses on how many Cubesats I can put on a Juno-sized mission? Yeah, that's right. You would have got it wrong anyway. 999. At this point, I said, whoa, okay. We actually decided to use, those are 1U CubeSats. We decided to use 333 3U CubeSats for two basic reasons. One is you need to come up with a clever algorithm as to how you stack the CubeSats in the launchers, because you're guaranteed to need the second one in or the third one in. And it's easier if we use 3U CubeSats. And then we also have a possibility of using 2 of the U's for batteries, because there's no way we can recharge the batteries once we kick them out of the dispenser. The mothership, and I think I have a picture, it's called PineSat. It looks a lot like a pine tree. The CubeSats are dispensed radially out of this thing. And we keep most of the basic architecture of the Juno spacecraft. We're going to use the same computers, same propulsion system, same solar arrays, et cetera. It fits the profile, what we wanted to do. And we also decided to keep as many components of the Juno mission as we could. That gives us a really nice looking TRL on paper. The software components, which is what we're supposed to be discussing here today, everything is Linux. Nice thing about being the dictator of the project, I can say that. We're going to put Linux on the RAD 750s. And we also put in a relational database. I'll tell you the importance of that in a minute. The CubeSat, each node has a lightweight copy of the database, and of course is running a core flight system. All of our housekeeping data is in the form of electronic data sheets, something I learned the last time I was here. And it worked like a champ. And I also had the advantage, one of the students was a database expert. And I'm not. I mean, if I have to do a database, I do it in Excel. That's about as far as I go. But she was extremely good at databases. And I explained the concept to her of electronic data sheets. And she said, yeah, sure, data. So that's exactly what we did. Each CubeSat had its own lightweight database holding its electronic data sheets. The mothership had a copy of everybody's electronic data sheets. For communications between the mothership and the CubeSats, if they're not deployed yet, we use wired, because they're already hooked up in there for power anyhow, so we'll just use wired communication on board the mothership. Once they get deployed, we use a short-range radio. Communications between the CubeSats that go out and the mothership is probably S-band. We didn't really work the trade-offs on that. The inter-satellite link is probably UHF. This becomes very important in a minute. And then the communications, of course, between the mothership and the Earth is probably a nice bundle protocol over X-band. They use X-band now. So in a sense, the mothership becomes kind of the store and forward node for all the various data readings we get back from the CubeSats. Now, multiple CubeSats give you a lot of advantages beyond 333-way redundancy. One is you can make simultaneous observations from different points of view. You can have one CubeSat plunge into the atmosphere and have the other CubeSats monitor what's going on while that's happening. So we have enough of them that we can send suicide missions in and get data back as long as we possibly can. And of course, the CubeSats all have different, not all different, but there's groups of CubeSats with different sensor sets on them. The bus is the same. The bus is identical. We'll have different sensor sets on different CubeSats. So the mission scenario that we worked out was, and a lot of the individual pieces were prototyped. We didn't build anything as big as Juno, but we were looking for proof of concept. During the cruise phase, the CubeSats are switched off. And periodically, the mothership commands them to be turned on one at a time. They run a functional self-test, and then we update the database. So if something fails, well, actually, right before we deploy it, we check to see if it's functional. If it's functional, we deploy it. If it's not functional, we deploy it. Probably just sending it into the atmosphere to burn up. But we would like to know that what we're deploying for a particular area is functional. Within the mothership, everything is networked. Upon arrival in the Jovian system, the mothership will go into orbit. Probably gravity gradient orientation would be best for the kind of things that we want to do. And we have to avoid the radiation belts as much as possible because the CubeSats are essentially unprotected. The on-site operation, target of opportunity, something we'd like to look at for sure. We select a CubeSat that has the correct sensor set and send it. First we run self-diagnostics, and then we send it off on a mission. It's dispensed fully charged from the solar arrays on the mothership, but it has, of course, a limited lifetime. There's not much we can do about that at Jupiter. So the mothership itself is, a 2,000 kilogram CubeSat. So it's going to have the same sensor suite and stuff like that. So we get one more observational platform in there. And the various CubeSats have varying instrumentation. And as I mentioned, CubeSat suicide missions are possible, returning data as they plunge into the atmosphere as long as they can. We got a lot of them. We can get rid of a few. The other thing that we postulated and we also prototyped is called a cluster of convenience, that within the mothership, all the CubeSats are networked, hardwired networked, and if we put the Beowulf software on them, now we have a 334-node cluster computer. And that would be NASA Goddard's Beowulf. This also allows predominantly, most important, the PNN, probabilistic neural network, which is another Goddard project that is extremely good at sorting data and finding patterns. What an interesting use. So we would use that. And we looked at using deployed CubeSats as members of the cluster, which you can do. There's some problems with that, mostly due to how far away they are and the communication delays and such like that. Obviously, you can use the remaining CubeSats when you start getting close to end of mission. You're running out of nodes, running out of compute nodes because you've just launched them. But we did look at some options that would allow us to use CubeSats in the vicinity as members of a node. And once you can do some software that looks for patterns, then you can send back more relevant data. Of course, the scientists say, we want raw data, don't touch it. And we'll say, well, we're going to touch it because we can send you back better product at that point. Besides, it's our mission. So, okay, so the EDS's electronic data sheets are instantiated in a relational database. So we have that both on the mothership and on each of the nodes. We actually prototype using SQL in the mothership and SQLite on the various nodes. And the nice thing about a database, and again, I'm not at all a database person, but I've been convinced that the position of a data item within the database is also a relevant piece of information. And it can cut down on your data transmission requirements. The data within our defined database was both static and dynamic. And the mothership, what did I mean, 7? I think that's a typo, a numeric typo. Oh, or unless those are model numbers. Oh. Okay, so the mothership is the carrier and the dispenser, 9.2 meters long, 1.8 meters in diameter. That's kind of what fits within the shroud of the Ariane 5. Dry weight of 2,700 kilograms, which includes our 333 CubeSats. That's what the dispenser looks like, and that's why we called it the Pine Set. Each of those little, I guess they show up as golden colored things here, is a 3U dispenser pointing out at a slight angle but radially. So we keep the Durad 750, which is up in the nose, I believe, of that structure. CubeSats are 3U. We can have propulsion because there is no primary payload. We're not endangering anybody. The concept that came from an earlier concept of most CubeSats are tag-along payloads or ride-sharing. And the reason they generally don't have propulsion is anything that squirts out liquid or gas is endangering the primary payload. But we said, gee, if we launched a mission which only had CubeSats, then we were only endangering ourselves, and we'll take that risk. I think the day after I said that, the Indian Space Research Organization launched a payload of 104 CubeSats. No primary payload. Another one of my ideas validated. I have to thank the Indians for that one. Okay, so the CubeSats themselves would be similar in design to Goddard's PiSat. They would be running Linux and CFS and also SQLite, and a copy of the Beowulf clustering software. Probably a smaller version of that, but we didn't dig into it. We only built one cluster with Raspberry Pis. So the CubeSats get deployed to targets of opportunity. One of those targets of opportunity on the previous Jupiter mission was when the comet Shoemaker-Levy entered the Jovian atmosphere and burned up. So there happened to be the spacecraft there that captured that whole thing. You couldn't have asked for a better opportunity or place to look at it from. So anyway, these can request help from the mothership if they see something interesting. Let's say it appears to be microwave, but they don't have a microwave sensor, then they can connect back to the CubeSat and said, send me one of my buddies that has the correct sensor set on it. I found something interesting over here. They can do radio occultation studies by being, let's say, on the opposite side and looking through the atmosphere at a glance back to the mothership. So there's some advantage to that. We can observe the same phenomena from various points of view. We can send them plunging into the ring system or the atmosphere. And as I mentioned, be able to address the targets of opportunity like Galileo did. Because you really can't predict some of these things until you get there, and then you want to be able to take advantage of them. The key software components being the virtual czar of this project, I said everything will be open source. Linux, the NASA Goddard software, Core Flight exec and system, the SQL database, and then Beowulf with its message passing interface and the parallel virtual machine. We also have another, this is to get your attention for a second, another item called rad-hard software. And you might say, wait, it's rad-hard to begin with, it's the hardware that fails. Yeah, rad-hard software is a concept that evolved out of what one of my students was doing in self-test, having the computer test itself functionally. And he was looking at the type of testing that the manufacturer does on the part, the database of known errors and known failures for the particular chip, and taking a look at the obvious stuff for radiation damage, like you see the current draw go up. So we were putting together, he called his project Sentinel, and it was running on the CPU that was the target, and it was trying to figure out if there was not just radiation damage, but any kind of malfunction on that CPU. We kind of adopted that and added a few things for the, like the radiation being probably the worst case scenario. So we had some software that could actually figure out we were having a problem before it became too bad and do whatever you could, which is usually a reset, and see if it worked or not, and then maybe just take that particular item out of service, because we can report back via the database that we've had a fault. Clustering software, as I mentioned, a Beowulf running the probabilistic neural network, which does a really good job with random data in terms of classification and pattern recognition. Yeah, the rad-hard software. So it's pretty much a suite of self-test and monitoring software based on past experience. It's passive. It might use CRCs across the memory, looks at the current draw for the radiation damage and such like that. It could also be, it has components that are active, such as memory scrubbing, reset if necessary, and it tries to do a test and remediate, does it a certain number of times, and it says, nope, you're out of the running. You're going to get plunged into the atmosphere at this point. So we can add to or change that after launch based on trending data, because the mothership is getting the data on the individual CubeSats continuously. They're not powered up continuously, but it's checking them as it's in the in-flight series. So if we see a particular problem that's occurring in 1 or 2 or 3 CubeSats, we might suspect a trend and put in a piece of software that would look for that particular trend that we may not have been smart enough initially to put in. So this is a research topic, and we did a little bit of it on the ground in terms of just putting together a system and trying to simulate some faults. CubeSat behavior, they can act independently. They're probably best at acting as members of a swarm. The collective behavior emerges from interactions between the members. This is a concept that came out of, again, NASA Goddard, from a guy I used to share an office with, actually. And it was in the late 1970s. And it was called, at that time, ANTS, Autonomous Nanotechnology Swarm, for the exploration of the asteroid belt. Because as many targets as we have at Jupiter, there's 100,000 targets in the asteroid belt. We don't know, we haven't counted them yet. But it's a self-organizing behavior like swarms of fish and bees and things like that. And the software is available for it. You get a very diverse, very agile architecture out of this. It starts trending toward finding answers to questions you haven't asked yet because you weren't smart enough. So it pulls a lot out of the data. It's very reactive to local conditions and to targets of opportunity. All units in this architecture are peers. There's no masters, nobody telling the entire swarm what to do. It's a very interactive behavior. So what's next? we're expanding on this a little bit for an asteroid mission, which is what the swarm software was originally designed for. The problem is we can't go further out than Jupiter because we won't have enough, one-way light time, and we also won't have enough solar power to do anything. And we're not going to put little tiny radioisotope generators inside the CubeSat. So Jupiter was, today is about as far as we could go with this. So we decided to pull back and take a look at the asteroid belt. It's a massive problem in terms of data items that you would actually like to observe, but it's a lot easier because regular solar cells will work fine on the CubeSats. We can use solar sails to get them to move around within the asteroid belt. So we can also get more CubeSats in. And 333 might not be enough, but we're not going as far, so we can actually carry more weight. That's the reference on the swarm approach. There's actually a couple references on it, but Walt Truskowski there is the guy that came up with that approach. So, any questions on this? That's good. That's about all I know. Okay.
Are you worried about Jupiter space junk?
We didn't actually address the space junk issue at Jupiter. I mean, the ring systems are big collections of junk, rocks and things like that. But we didn't actually consider it for this. I mean, that, if we were actually doing a mission, we would certainly consider that an issue. Because it's going to be tricky to get an orbit that keeps you out of the main radiation areas without getting into one of the ring systems. So it's an issue. Okay. Oh.
Yeah, sorry if you mentioned this, but a question about the, over here.
Oh.
The Beowulf software that you'd mentioned, does that cover the ad hoc internetworking
The Beowulf?
aspect of this CubeSat cluster? Or like, how would that
Beowulf, yeah.
self-organize?
Beowulf is a clustering software getting everybody to work together at the same time with the communications part of it.
Okay, so like links going in and out and little,
Yeah.
Cool, okay.
Yeah.
I didn't know I could do all that.
And it's off the shelf and it's open source. What more do you want? Okay. What's it? Oh, yeah.
Quick question.
One more? Oh, one more.
yeah, one
Okay.
first.
Yeah.
You mentioned you were using SQLite for the CubeSats.
Yeah.
You know which database system you were using on the mothership?
We're using our base on the mothership. And, not our base, I'm sorry, SQL on the mothership and SQLite on the CubeSats.
Well, SQL is the language definition. It's not necessarily a specific
Oh,
database.
well, there is a product called SQL.
Oh, there is?
Yeah,
Okay, thanks.
right.
So I assume you looked at the RAD 750 because of the radiation issues that far out.
Yeah.
But the power consumption on the RAD 750 is going to be the other side of that. And so I guess by moving into the asteroid belt, you could move into lower power processors, because like Dawn, I don't think had a RAD 7. It had other processors. I know there was a Leon 2 on it, for
Yeah.
example. So
Well, I mean, the RAD 750, we said this is going to work. This has worked at Jupiter. Let's leave it alone. Yeah, it's power hungry, but the arrays, the solar arrays, were sized for that, so it wasn't really a problem.
But at Jupiter? But
At
you don't-
Jupiter, yeah.
So, okay, you get enough sun to run a RAD
Yeah.
750 at Jupiter. Okay.
Yeah, 3 of them actually. Yeah, very efficient arrays, very, very efficient. If we went to the, just went to the asteroid belt, we would redo that. I doubt if we would need the RAD 750. We would probably just put a couple of CubeSats in charge of the mothership.
All right. So, are there more questions or are we moving?
Okay.
Thank you.